Hello. In this video we will examine how students can use ClassWiz to support their early understanding of derivatives. Turn on the ClassWiz and let's set it up. We'll start by using table mode in this video, so choose this mode with menu and 9. In this video we'll look at two ways in which ClassWiz can help students understand the idea of a derivative at a point and a derivative function. When students first encounter differential calculus, they already know about the gradient or slope of a line, which describes how the values of a function are changing. In the case of a linear function, the values change in the same way everywhere, but other functions are different. Let's consider a quadratic function, f at x is equal to x squared. We'll make a table of values between -4 and 4. -4 to 4, just in steps of 1. And here's our table. If we scroll the table, it's clear that the function values change differently. Between -4 and -3, it goes down by 7. Between 0 and 1, it goes up by 1. Between 3 and 4, it goes up by 7, and so on. So let's look a little bit more closely to see how this change is not uniform. Let's think about the change from 1 to 1.5, so we can change this to 1.5, and maybe from 1.5 also to 2. And we can see that from 1 to 1.5 the change is 1.25 between these two values, and between 1.5 and 2 the change is 1.75. So the change is not uniform. Of course, the students know that the graph is curved and not linear. Let's take a closer look at how the function changes near the point where x is equal to 1. So we'll go from 0.5 to 1.5 in steps of 0.1. And we can see here, as x goes from 0.9 to 1, the function increases by 0.19 between there and there. And between 1 and 1.1, it increases by 0.21. So let's take an even closer look. Say from 0.9 through to 1.1, and a smaller step of 0.01. And let's look down here, as x goes from 0.99 to 1, and from 1 to 1.01, the change appears to be close to 0.02. And between 1.01 and 1.02, it's almost 0.02. So let's look closer still. So 0.99, closer still to the point where x is equal to 1. 1.01, and now choose a much smaller interval, a smaller step. And let's get close to 1 down here. So you can see here, as x goes between 0.999 and 1, the change is almost 0.002. And this one is 0.002 and 0.004. It's about twice as much as the distance. So in this way, students can build an intuition about the idea of getting closer and closer to something. In thinking about these changes, students can be helped to see that close to the point where x is equal to 1, the gradient of the function is close to 2. When x changes by 0.01, the value of the function changes by twice as much as that. So it's instructive to consider another part of the curve to think about this as well. So in a class, students could all look at a different point in this way. So let's choose a different value, say close to when x is equal to 3. So let's try from 2.99 up to 3.01. That's close to x being being close to 3. And let's have a gap of 0.001 each time. Now when we look at the table, close to 3 down here, we can see a small change of x of 0.001 leads to a change of 0.006, 6 times as much in y. And another small change of 0.001 leads to another change of about 0.006, about 6 times as much. This kind of activity can help students to think about ideas of getting closer and closer to a point, and also help them to see that if you look closely enough, a curve looks like a line with a constant slope. These are important understandings to build for the idea of a derivative at a point. Now let's change our class whiz into calculate mode with menu and number 1. Class whiz has a numerical derivative function which students can think of as a way of finding the slope of a curve at a single point. And here it is here above the integral key, shift and the integral key. And let's consider the same function we've used so far, the one you can see in the bottom screen here, f at x is equal to x squared. So we'll enter the function there and move across with the cursor to find the derivative of this function when x is equal to 1. And students can think of this as the slope of the curve when x is equal to 1. And you can see the result in this case is 2. The derivative function can be used for other values such as x equals 2. The easiest way to do this is to use the replay facility with the cursor here. And I'll backspace and change that 1, the delete key, and make it 2. And other values can be checked in the same way. I'll do the same thing. Use the replay key, backspace the 2, and get a 3. And this result of 6 is consistent with what we observed previously in the table. If we continue doing this, and I'll do it another time, delete and change the 3 to a 4, most students will recognise a pattern of results here. And a good way to see the pattern is to use the up arrow to see the set of results. Let's do that now. You can see the arrow here is pointing upwards. So there was the first one. When x was 1, the derivative was 2. When it's 2, it's 4. When it's 3, it's 6. When it's 4, it's 8. Many students will see that the slope of the curve for f at x is equal to x squared seems to be twice the value of x, so that the slope is increasing as x increases, which is consistent with their understanding of the shape of the parabola. In the same way, if negative values of x are tested, the slope will be negative. Let's try one of those. Delete the 4 and change it to negative 2. And the slope is negative 4. And similarly, when x is equal to 0 at the origin, delete the negative 2 and change it to 0, the slope is 0, which is consistent with the student's intuition and observations that the curve is horizontal at that point. This kind of experience is building the conceptual groundwork for the idea of a derivative function. Of course, similar ideas can be tried with other functions, although the pattern is clearest at first with the quadratic function, which is likely to be already familiar to students. Students may be surprised to find that other functions produce the same results. So, for example, if we change by using the replay key, change x squared to make it x squared subtract 1, we get the same results for the same values of x as before. When x is 2, then the derivative is 4. And when x is 3, the derivative is 6, although the function is different. The idea of exploring patterns can be productively continued through using a table, or we could use a spreadsheet for a similar purpose. The numerical derivative function can be used in a table to construct patterns, Let's see how to do that by switching to table mode with menu and number 9. So let's consider again the quadratic function, the one we've got on the screen here, and we'll tabulate its derivative at various points. So let's start by putting the derivative function in here. X squared is the quadratic function, and rather than a particular point here, we'll put just x to indicate a whole range of points. And we'll choose, let's say, from -10 down to 10, up to 10, in steps of 1. And here we can see the derivative at many values of x. And the pattern here is quite clear. When x is -10, the derivative is -20, and students will not have much difficulty seeing, as they scroll down the table, that the function values are twice the x values each time. Most students will find this pattern very clear. The value of the derivative is twice the value of x at all points in the table. And if we tested that by changing a value, we're going to change this value 5 and make it, say, 7.4, then the derivative is twice as much as 7.4, 14.8. A good test of whether the pattern has been observed is to use the second function to show it. So tap clear, we'll leave that one as it is, and we'll use the second function, which in this case it looks as if the derivative is simply 2 times x. And students can test their prediction by doing things like this. So let's generate the table, and sure enough, here's the derivative function, and here's the guess as to what it might be. So we've shown these learning possibilities using one particular function, y is equal to x squared. But the ideas can be explored with other functions as well, of course. Consider, for example, the function y is equal to 3x squared. And let's see what happens. The first one is the derivative, and the second one is the guess, but no longer is it correct. But if we were to change the guess to 6x, then the derivatives in the f at x column and the guess in the g at x column are the same. So the pattern of derivatives is different from what it was before, but most students will have no difficulty in seeing that this value is 6 times that one. As another example, consider this function. Y is equal to x squared add x. So we'll go back and change the function again. I'll edit it a little bit. X squared add x. And leave that where it is for the moment. And here we can see that there is a consistent pattern for the derivatives in the function column. And certainly the pattern seems to be that the values are going up by 2 each time, starting with 1. So the derivative function looks as if it's 2 times, and we can go and check this, 2 times x add 1. And now let's check that prediction. Yes, indeed, the second column here has the derivatives, and the third column has the guess. And we can see that those are the same. Each time the value in the derivative column is, in this case, 2 times 5 add 1, and this is, of course, 2 times 5 add 1. So the two are the same, and the derivative function is y is equal to 2x add 1 for this function. Work of this kind has a lot of potential to both make sense of the idea of a derivative function, but also to see some of the properties of derivatives without an excessive focus on algebraic rules. That's the end of our adventures with derivatives. Students can use ClassWiz with other functions in similar ways to build the essential ideas of a derivative at a point and a derivative function. You'll find Module 15 of the ClassWiz book also contains information on how ClassWiz can be used to deal with various aspects of derivatives, including some of the properties of derivatives, as well as detailed explanatory text which can be copied for students as well as teachers. The module includes some exercises to check efficient ClassWiz use, some examples of activities to suggest educationally valuable things to do, and some guidance for teachers. You can download this book freely from the Casio Worldwide Education website. Happy calculating!